5 trapezoidal sums. So we've done rectangular sums, and now we're going to do trapezoidal sums. So this isn't, it's new, but it's not new at the same time. Use the trapezoidal rule with n equals 4 to estimate the area from 1 to 2 of x squared dx. Compare the estimate with the value of the actual answer. So they're saying use a calculator to get the actual answer, and we'll see how much error we have or how close we are. We're going from 1 to 2 with 4 subdivisions. So we should go every fourth, right? And there's 1. If I start at 1, 1, 2, 3, and there's 4. So let's draw some trapezoids. So we have the 2 bases, and then we finish the trapezoid like that. And these should be perfectly, the same width. So there's another base there, and then here forms the last trapezoid. So you can see that that edge of the trapezoid is following the curve very closely. This is going to be a pretty good estimate of the area. Now this is 4 fourths, this is 5 fourths, 6 fourths, 7 fourths, and 8 fourths. So it's really fourths. Those are x values. The area of a trapezoid is 1/2 times the height times base 1 plus base 2. So we have 1, 2, 3, 4 trapezoids. Let's get the area of the first one. That's going to be 1/2. The height is actually 1/4, from 4 fourths to 5 fourths. So 1/4 is the height. And then base 1 is what we would get if we plugged 1 into the function, because these bases, they're following the function value. So if I plug 1 into the function, we get 1 squared, and then plus the other base is what we would get when we plug 5 fourths into the function, because it's going up to that y value. So 5 fourths squared. So there's the first trapezoid. Now we got 3 more. So we're going to go plus 1/2 times 1/4. And now we're going to reuse 5 fourths again, because now this side is a base of the next trapezoid. So we're going to do 5 fourths again. And then the other side is going to be what we get when we plug in 6 fourths, or 3/2. So 3/2 squared. All right, we got 2 more. But now we're going to use this base again for the third trapezoid. So we'll reuse 3/2. And then we do this one. And the length of the base is what we get when we plug 7 fourths into the function. That's why we're squaring it, 7 fourths squared. All right, now here's the last one. It's still 1/2 part of the formula. 1/4 is the height. And we have 7 fourths squared, and then finally the 2 squared. That's where we end it. So this side's only used once. Now, if all the heights are the same, we can simplify this a little bit. We don't have to go through all of this. First of all, it looks like we have 1/8 in all of them, and it's multiplication. So let's factor out a 1/8. And there's a reason I'm doing this. I know I could plug this in the calculator and get an answer, but we're trying to develop this method that we're going to use and make sense of it. Notice that we only use 1 once. We only use the left side once, right here. And so we have 1 squared. But everything in the middle, we use twice. There's 2 of these. And not only that, if I'm factoring all of this out, all that's left is addition, addition, addition. Everything that's left is all addition. So now I can go 2 times 5 fourths squared plus 2 times 3/2 squared plus 2 times 7 fourths. I'm going to run out of room here. But then plus 2 squared. So you only use the first one once and the last one once, but everything else in the middle you use for 2 adjacent trapezoids. So that's why you're going to see a 2's in the middle when we look at it. And you can see the bottom of your page down there where you see the 2's in the middle. Well, that's because they're sharing a side. Should we get an answer at least? Let's see, 1/8. 1 plus 25/16, so 50/16. Plus 9 fourths, 18 fourths. That probably reduces, but who cares? 49, so 2 times 49/16, whatever that is. I'll let the calculator do the work. And then plus 4. All right, I think I mess up. I don't remember that answer from earlier today. Did you guys get that? Anybody try it? Nobody tried it? Thanks. What'd you get? I don't think that's it either. I don't think. It might be, though. It might be. I got the 1/8. 1 plus 50/16 plus 18/4. Maybe it is right. Oh, it is? Okay. All right. All right. I just didn't recall it. Anyway, we could have done this. Math number 9. We're going from 1 to 2. We probably could have just decided if it's right this way. X squared with x. We'll compare it to the actual answer. Oh, yeah, it is right. It's only 1/100th off, right? Roughly. So it's actually 2 1/3 is the answer. So there's your approximation. I was right all along. Well, there's the actual method, and it depends on, your height has to be the same all the way through. And you can see we only multiply the first y value. You plug a function value in, you get the y value. We use the first one and the last one once, but everything in the middle is used twice for those adjacent trapezoids. Example 2, then, is not the trapezoidal method. It's use a trapezoidal sum. So actually I should put sum here rather than method, because the method requires all the heights to be exactly the same. Well, if we're going to go from noon to midnight, what we're trying to find, let me read it. An observer measures the outside temperature at various times from noon to midnight, recording the temperatures in the following table. Find the average temperature for the 12 hours. So we're going to take 1 over 12. We're going to multiply times the integral from noon to midnight. We'll say 0 to 12 of some function dt. But what we don't have is we don't have a function. So we're going to take 1/12 of the area under the curve, and we're going to estimate that area using trapezoids. So that's the 1/12. Here's our trapezoidal sum. It is 1/2 times. Well, the height from noon to 2 is 2, and then we do 63 plus 66. So there's the first trapezoid. Now we can't do the method because noon to 2 is 2 hours, 2 to 4 is 2 hours, but 4 to 5 is 1 hour. So this becomes very tedious. But then 2 to 4 is 2, and we use 66 plus 70. And then 1/2 times 1, 70 plus 69. 5 to 7 is 2, 69 plus 68. 7 to 9 is 2 hours, 68 to 64. And then finally the last one, plus 1/2. Noon to midnight is 3, 64 to 55. Example 2. 65.17. They only go to 2 decimal places. Shame on them. We would go to 3. However, does 65 seem like a reasonable average looking at those numbers? Does that seem reasonable? Yeah, I think so too. So if you did all the math and you got 108 for an average, you probably messed something up, right? You should be able to look at it and go, yeah, it seems like a reasonable average. That seems like right down the middle somewhere. Anyway, I didn't want to type all that in. You okay with that? Right? Okay, good. Me too. I cheated a little bit. Simpson's rule is I think it's fascinating. I've seen the proof. I'm certainly not going to develop it for you. But just in general, if you have this curve, it uses parabolas So it uses parabolas to kind of estimate the curve. And when the curve is curvy, it does a great job. When it kind of flattens out, then your parabolas don't do such a great job. But imagine having 1,000,000 parabolas to estimate it. It would be hugging that curve very tightly. So it's a very accurate process. So here's what it is. Instead of having 1/2 times the height, first of all, we take 1/3 of the height. So it'd be 1/3 height. The beginning and the end are still all by themselves. And then the pattern is you start with a 4 and then alternating 2, 4, 2, 4, 2, 4, and you keep going. Now, the one condition we have on The Simpsons is that you have to have an even amount of subdivisions or subintervals, which you don't have to come up with. They'll tell you. And our example has 4 subintervals because it needs to be even. All right, but otherwise it's exactly the same stuff. So we're going to use Simpson's rule with n equals 4 to approximate just 0 to 2 of 5x to the 4th. So if we're going from 0 to 2, 4 subdivisions, each is a half, right? 2 units cut into 4 pieces. 1/3. Each height is going to be a half, so times a half. And then times, well, now here's our heights, or excuse me, our bases, right? Here's our bases. And so we're going to plug 0 into this, and I know it's 0. But there's the single one, and then it starts with a 4. Then you go 4 times 5 times 1/2 to the 4th. So there's plugging in a half to get the other base, to get that base. All right. And then plus 2. The next one is 2 times 5 to the 1/2 to the 4th. Not 1/2. 0, 1/2, 1. Excuse me. 2 halves. Plus 4 times 5, 0, 1/2, 2 halves, 3 halves to the 4th. And then finally, the last one is all by itself. So the last one is 5 times 2 to the 4th, like that. So it starts as a single, it goes 4, 2, 4, and then a single. Three halves times 0, 20 times 1/16 plus 10, yeah, that's nice, plus 20 times 81/16 plus 5 times 16. That's not it. Oh, I did that. That's not it. I was doing great this morning. Now I can't get it to work. 20 times 1/16, I like that, plus 10, I like that, plus 20 times 81/16, plus 5 times 6, what? 3 halves, what's that now? Oh, 1/6. Thank you. I promise I was doing this right this morning. 1/6. Finally, third time, that's it. Because if we go math number 9, we go 0 to 2 of 5x to the 4th. That's very close. We're only off by 0.08. So it's pretty close. A, use the trapezoidal rule with n equals 4 to approximate the value of the integral. B, use the concavity of the function to predict whether the approximation is an overestimate or an underestimate. So let's kind of summarize this. Let's go with rectangles. Let's talk about B before we do anything else, because I really haven't mentioned it yet. Let's talk about rectangles. If you have an increasing function, concave down or concave up, it doesn't matter. Left endpoints will be what, an underestimate or an overestimate? Underestimate. So on an increasing function, LRAM, we'll just say is an underestimate. RRAM, if we go right endpoints, it doesn't matter where, right endpoints, can you see that that's going to be an overestimate? So an overestimate. Decreasing is going to be opposite. It doesn't matter whether it's concave down or concave up, your left side will be an overestimate. So now LRAM on a decreasing will be over, and RRAM will be an under. Notice we don't talk about midpoint. That's so close. There's a little bit over, a little bit under. They don't ask you about that. This is very clear. MRAM is not. For trapezoids, now it's concavity that matters. If it's concave up, and if we used one big trapezoid to estimate the area, can you see that's going to be an overestimate? Okay, so for concave up, that's going to be an overestimate. And for a trapezoid, it doesn't matter if it's increasing or decreasing, but concave down is going to give you this underestimate. So concave down gives you an underestimate. So you could be asked about any of this or all of it on the test. So be ready to answer that. I think we're going to review that on Tuesday as well. But you'll have to know it for the test. Just takes a little bit of just a little sketch to realize what's going on. All right, let's try letter A. You try it. Please. So 0 to 2, and they're asking for 4 subintervals. That's going to be, first of all, a half. And then if I'm going 0 to 2 with 4 subintervals, I'm going by a half each time. And now I need the first value plugged in. That'll be 0 squared. And then 2 times a half squared. Plus 2 times 1 squared. So that's 0, 1 half, 2 halves, 3 halves, plus 2 times 3 halves squared. And then finally, we don't double the last one, and that'll be the 2 squared, like that. And then we just need an answer. So I'll try to do it right this time. 1/4. I got it. 2 times a fourth, a half. Plus 2 plus, I'll just go 2 times 9/4 plus 4. Whoops, I missed the plus. Plus 4. 2.75. B, x squared is concave up, so that's going to be an overestimate. We're going to have too much area. And letter C, find the exact value. So math number 9, we're going from 0 to 2. X squared. 2 and 2/3. So you can see that that actually was an overestimate. It was too much because it was concave up. Any questions for the good of the cause? All right, last one. Now we're kind of bouncing back and forth between stuff where we can do the method and stuff where we can't, because the heights aren't going to be the same. This is a height of 1, 2, 1, and 2. There's a pattern for sure, but it's not the same. It needs to be the same. So we're going to go 1/2 times. The height between 2 and 3 is 1, and then we have 16 plus 19. 1/2 of 2, and then 19 plus 14. And it's tedious, to say the least. So there's 14 and 13, and finally the last one, 2 is 13 and 20. Very tedious when the heights are not the same. So we have 1/2 of 35 plus 33 plus 1/2 of 27 plus 33. I get 97. Hey, I got that in one shot. I've been getting that all day. 97 is an estimate of the area under that function from 2 to 8 if we're just given that table. That's the best we can do. I mean, with trapezoids, it's the best we can do. Function f is continuous on the closed interval and has values that are given in the table below. Using the subintervals 1 to 4, 4 to 6, 6 to 7, what is a trapezoidal approximation of 1 to 7? All right, well, 3, 2, and 3. That's a bummer. I wish they were all the same. So a height of 3, base 1 is 10, base 2 is 30. Height is 2, 30 plus 40. And 1/2 times 3 and 40 plus 20. So we have to do individual trapezoids when the heights are not the same. Three halves times 40 plus 70 plus 3 halves of 60. Oh, I messed this up too. Dang it. Is 1. Don't ask. Don't ask. All right, what does that put? That puts us at. Oh, just 60. No, half, 30. 30. 160. Yep, that's it. Thank you. I must be getting tired. That's my excuse for today for making mistakes. I'll come up with a new one on Monday. All right, but I think I can get number 2. And I'll bet you can't. That'd be my bet. Anybody want to prove me wrong? Matt, come on, buddy. You came through yesterday. I haven't shown you this one. That's why I'm saying I bet you can't do it. That's my fault. It's not your fault. That's my fault. Let f of x be an antiderivative of sine to the cubed of x. If f of 1, what is f of 1? What does it mean when it's capitalized? It's antiderivative, isn't it? So that capital letter is suggesting antiderivative. So if antiderivative when 1 plugged in is 0, then what is f of 8? What do we get when we plug 8 into the antiderivative? So this one is, we're going to integrate from 1 to 8 of this function, sine cubed x dx. The second part of the fundamental theorem of calculus, says that in order to evaluate this, you find the antiderivative, that's the capital part, you plug in the top value, then you plug in the bottom value into whatever that antiderivative would be. So let me ask you, are you okay with me writing this out? Is everybody all right with that? That's exactly what we've been doing. We've been finding the antiderivative, plug in the top, always subtraction, plug in the bottom. But they tell us what f of 1 is. It's 0. So instead of putting this, I could put a 0 here, or a 5 there, or a 10, or whatever. So now to finally find out what f of 8 is, I just add the 0 over, or add the 2 over, or add the 5 over, whatever they tell me it is, and I can do this on the calculator, and we got the answer. So because that's a 0, all I need is that right there. 1 to 8 of sine to the third. So x raised to the third power. X, I love this question. What a great question. And then it's b. It's b. Someone told me this morning, why don't you just plug 8 into sine third of x? I go, how do you know that? He's like, I don't know, I'm just guessing. Okay, well, at least that's honest, right? So if you just plug 8 into this, they're real nasty to you. That's that one. They have that, in case that's what you just decide to do. That's pretty sneaky of them, isn't it? But anyway, it's not that. Well, we found that out this morning. I wouldn't have known that. But someone said, plug 8 in. I go, okay, let's do it. And we did it. We found that answer.